And here we have, these are temperature sensors that you can thread into a piece of pipe. And then we have some accelerometers for doing vibration measurements. Okay, these are temperature sensors that you can glue or stick onto the surface and make a measurement. And this is a typical connector that would be used. As you can see right here, it's threaded, and this connector kind of clicks and locks when you put it in place. This particular connector is for a pressure transducer, and what you have is there's 6 pins. Here's the function of each pin. Now down here you see this has got, it's called a shunt calibration. And what you do is you take a resistor and you shunt it into the system so that it generates like a 70% of the full scale output measurement, so that you can get an idea that the sensor's still working, still alive. Okay, so now we'll go through a design process to pick this sensor. You'll get a measurement requirement from somebody. So what are you trying to detect? And what is the range that you want to detect this stimulus? Where is this sensor going to live? How fast do you need to make the measurement? And how will you measure it? And what are the sensor interfaces going to be? How many pins in your electrical connector are you going to have? And do you need to use a clamp, or are you going to have some feet where you can screw it down? Are you going to have enough area to put that sensor? So let's go through the solid rocket motor pressure transducer design concept. So this particular transducer is called the operational pressure transducer, and it's used to tell the STS that the solid rocket motor has used up all its thrust. So we want to measure the pressure with an error of plus or minus 1% full scale output per system requirements. For this application, the range is going to be 0 to 1,000 psi. That means pounds per square inch atmospheric. Response time is estimated to be 1 millisecond. And our operating environment is going to be high temperature, it's going to be reducing, and you're going to have gaseous combustion products. Now when I say a reducing atmosphere, that means it's looking for oxygen. You could have an oxidizing atmosphere that's looking for something to combine with it other than oxygen. So first thing you want to do is a trade study. What type of mechanism are you going to use? So first we would look at a Bourdon tube, because it's highly accurate and precise. This is what a typical Bourdon tube looks like. But unfortunately it's too fragile. It wouldn't withstand the environment. So therefore a most rugged method would be to use a diaphragm with a sensing element attached to the back side. So the sensing element could be one of several methods: a bonded strain gauge, an unbonded strain gauge, a potentiometer, or a crystal. So what are the mechanical interfaces going to be? Well, in this case, the fitting will be determined by the subsystem mechanical or structures group. But it's typically a 37-degree flared fitting with a quarter AN thread. Now AN means Army Navy. So it's gonna have a double seal design. That means if it breaks one seal, there's a second seal to keep it contained. Same thing with the secondary pressure vessel containment. This is a fail-safe item. And then there's gonna be some secondary structure. You're gonna have to mount it with on a bracket somewhere, and then you're gonna have to have a sense tube running to that sensor, and it's gonna have to be fastened somewhere. Then what are the electrical interfaces? Is the sensor gonna have signal conditioning inside of it? If so, it's gonna have to have all these features. And then you'll have a 6-pin electrical connector. So here's some other considerations. The sensing element should be temperature compensated. The diaphragm should have a baffle in front of it to prevent direct exposure to hot gases. The transducer housing itself should be located in a relatively benign environment. And the transducer should be easily accessible. And the design should incorporate methods of in situ diagnostics. Now, one method would be the shunt resistor. Okay, inputs and outputs. So this list is needed by the software folks. They need to know we'll give them the range and tolerance, response time, and what the critical nature of the sensor is. Crit 1 means you got to have it to fly. Crit 2 and Crit 3 are you don't really need it as much. So I think I already talked about the operating environment here, or at least exposure. So thermal, is it going to be in a cryogenic, ambient, or hot environment? How much vibration is it going to be exposed to? What are all the fittings and fasteners and things you're going to need? Is there enough room to put it in there? And where are you going to locate it? So the output, what we do is we'll generate either a source control drawing or a specification control drawing. Now, a source control drawing is used to limit the procurement of a vendor designed and manufactured part to a source that exclusively provides the performance, installation, and interchangeable characteristics of the part selected. And it usually has a picture of the device in there. And a specification control drawing is on the same size paper, but it doesn't include a picture. I guess that's a more simple way to say it. Maybe I'll revise the charts. Okay, now I think that's the end of my talk. But anyway, what's next for NASA is hopefully SLS. So as you can see, it's got a capsule on top here. All right, so thanks for your attention, and now go forth and do good work. You guys have any questions?
It's very detailed.
Any questions?
So you say that you classify yourself as a physicist, but your job title is an engineer.
Yes.
Did you take any or all